Okay, so now we go to the next lecture. It's Professor Antonius Armaou. He did his diploma in chemical engineering from the National Technical University of Athens and his PhD from the University of California in Los Angeles. He is currently Professor of Chemical Engineering at Pennsylvania State University, as well as University of Patras in Greece. His research interests lie in the model order reduction approaches, optimization, and control algorithms.
Thank you very much for the kind introduction. So, today I'm going to discuss about some of the problems that we like. Today I'm going to discuss about some of the problems some of the problems that we have. Some of the new processes that we would like to investigate, based on optimization. And this is a collaboration work with Professor Jensi here at the Young University. Currently, this is your work, it's going to be switched then. So, sorry. Okay. Now, around the time that CU was creating the control systems engineering section, people were trying to further work on polymerization, and they started thinking about controlling polymerization. This led to the current search on this works on the precision polymerization, where the objective of the polymer, the process is to create a tunable molecular distribution, a molecular weight, to have envelope functionalization and have a tuned molecular weight distribution and be able to achieve complex topologies such as those that I'm presenting here, where the simplest one that we can think of is a tie block. And in general, we want to have multiple polymers. And star polymers is a very interesting construction. Sequence-defined ones, and I would like to call your attention to hyperbranch, also polymers. The applications that drive the need for polyprecision polymers are coatings and membranes, pharmaceuticals and medicine, energy, advanced analysis, and faulty materials. The processes, there's actually currently a need for processes that can achieve precision polymers. And for the process to be successful, you need to have a way to manipulate the equilibrium, have predictable blending of the constituents in order to create the polymer that we care about, have programmable initiation, which does have an effect on the molecular weight distribution, and have controlled reaction sequence. Out of the processes, a family of chemistries that are interesting are the reversible deactivation metapolymerization chemistry, which is it's a family of processes. And the main two reaction schemes that we have found are the atom transfer polymerization and reversible addition fermentation polymerization. Those are examples of RDRP, where the idea is to actually have a dormant polymer forming, which we can activate then on demand. These obviously are not simple processes, and there is a host of needs. There has been great effort in the last 20 years and intensive research on the chemistry where chemists have created new monomer, novel initiator, novel activators and deactivators in order to exactly create those polymers, and have chemistries that are insensitive to oxygen, side reactions, and be able to have reduced use of metals and sulfur species. The idea of RDRP is actually to have those, to have a blend of the monomers and be able to create the, for example, in this case, the polymers that we care about. The chemistry that has created, the chemical systems that have been developed, have actually created pure process chemistry where we can actually have external stimuli drive those reactions, such as voltage potential, welding with light, and that will lead to a control distribution, ultrasound, and biological stimuli, such as enzyme initiated drug. The problem, and one reason why, even though there are 4,000 patents and more than 30,000 papers in the last 30 years on precision polymers and RDRP, is the fact that there has been a proof of concept, but there's everything that we see are in the labs here. And I maintain that this is the great time now for process systems engineering in order to be able to move beyond the lab scale and manage to design processes so that we can actually have both standard batch processes at the scales that we care about, large volume continuous processes and 3D printers at the industrial stage, that is industrial level. So this brings forth the need for process design and scale up, and the problem, the underlying problems that we have to solve are problems of dynamic optimization and regulation. Now, borrowing from a group Juno, we can see that there is a need to somehow create a model for such processes, and this means for the need for us to put our reaction engineering hat and be able to create, to be able to identify the genes kinetics, and the genes kinetics that we may have, and physical limitations, and then link that to the external regulation to the different stimuli that we have for these chemistries, and also focusing our attention on what we care about, which is the polymers, so that we can actually also identify the chain microstructure in order to be able to optimize this process. So, we will exemplify this work using an example, which is an APRP example, using a standard batch process, using light as our external stimuli. Now, for those of you that are not familiar with APRP, let's present a simplified APRP scheme. What happens is that we have our initiator and our activator, which then, what does is it actually activates the dormant polymer. And it produces a radical which then keeps on growing until the growth terminates to some resistant side reactions or due to the consumption of the radical and the consumption of the monomer. What happens, though, is also that as we are the reaction proceeds forward, we have an accumulation of the deactivator, which then drives the slow down the reaction through a deactivation step. As a result, this after a while, this process slows down. It has the advantage, it does have the advantage that it has very controlled polymerization, we have very nice molecular weight distribution that we are going to get with very low molecular weight distribution deviations. Now, the problems that we may run into are that we have a high concentration of the deactivator, which is something that we don't care about when we create a polymer. So that's where actually the external stimuli come into place, where the activators can actually be generated through light radiation, bypassing now the need to have the concentrations of the catalyst and bypassing the need to then bypassing the problem of having largely activated concentrations. Now, the secondary question is, we have our process, what do we care about? Well, we care about being able to understand the microscopic properties of the polymers. As a result, when we create models in order to run optimizations, we do need to have, we need to choose some of our properties, microscopic properties, in order to focus on them, such as the molecular distribution, the composition distribution, the composition distribution, and the sequence length distribution, just so that we can actually have either so that we can actually identify and characterize the block copolymers or branches of copolymers. We also need to keep track of macroscopic properties, such as the double average chain length and weighted average chain length and expressive index. And this mobile information will give us a more accurate understanding and will characterize the status of the polymer, the microscopic stability and mechanical strength. Now, modeling the microscopic properties requires us to consider stochastic methods for our parameter constraints in our optimization. The advantage of stochastic constraints is that stochastic methods are usually equation-free and they are easy to modulation of light radiation, and they are capable of describing the dynamic microscopic properties of polymers. The disadvantage is that simulating the dynamic polytherapy systems has significant computational costs, and the nature of the uncertainty produces challenging in the optimization task. What we would care about is to actually use the deterministic method, where we have to develop more advanced operations, which is straightforward, and it has an efficient calculation of the system states and polymer properties. The problem is describing the dynamic cost of the regulator of light radiation using operational speciality and solving large-scale differential regulator operations in order to get those microscopic properties is challenging and usually leads to very stiff large systems that are computationally efficient. So the goal in order for us to be able to do system engineering is to either model this dynamic of the process at the microscope at the same time efficiently with the dynamic of the cortex. So, let's first talk about the straightforward way. How about using dynamic Monte Carlo simulation in order to simulate a polytherapy process? Dynamic Monte Carlo simulation is based on probability theory, where every step in the polymerization process becomes a random throwing the dice, and that's a random process. So we go from initiation to propagation up until the time we reach a termination. The problem is, in order for us to have accurate results, we do have to have large sizes of our population in order to be able to draw the proper conclusions and predict the microscopic structure well enough. Okay, so we think about what happens in the dynamic simulation. We have the first half the initialization step, followed by an incremental progression in time through reaction selection, system state update, and continually cycle through the simulation methods. Now, it is a straightforward way to model the process. The only problem is, that it takes a long time. So here is a proof that we can actually do model the process where we can see for different conversion values as the process is evolving, the molecular weight distribution. We can also see the rate fraction of our polymers, and we can also model the other properties such as the jet polymers versus the normal polymers oxidation. And another thing to note here is that the process evolves very fast, reaching then a quasi-steady state, and then it slowly evolves back. And one thing to also notice here, the complexity. This is the simple photopolymerization for a photopolymerization process where we have a number of different reactions that we need to keep track of, and we also have a number of conjugated reactions that we also need to keep track of. This simulation was done using constant line deviation, which is baseline for our presentation work. Now, if you think about photopolymerization, one great effect in order to be able to create a precise polymer is this ratio between activation and deactivation. And this equilibrium constant and the way we manipulate it is exactly what induces the precision, and also what induces the very tight distribution of the molecular weight. Now, we also need to investigate the effect of this equilibrium constant on the level of control and the impact of the deactivated concentration on the level of control. So, for this value and the concentration of this value. So, using the specific simulation, we can see that the equilibrium constant has a significant effect on the controllability of this process, where we see that for very low values of ATRP, we have almost no control on slowing down the process. So this is the lighted period versus the dark period, and we see that we keep on having a growth of our polymer. While for higher values of this equilibrium constant, which means that we actually don't have as rapid difference between the activation and the deactivation constants, we have a much better control of our slowdown, and we have better control of tolerances, which is something that we care about, obviously, because we need to have control of the slowdown in order to be able to get the slow volume. So, we see here that finding the proper gate is not something trivial, and we need to, in our optimization, consider that equilibrium constant. We also see here that both using the method of moments and our dynamic vocabulary, we have excellent confidence. Now, another thing that we want to see is what happens if we have a too high activator concentration. Having a higher value of activator, so that we say that we have a higher acceleration. But this also leads to loss of controllability, since a very high concentration of our activator, and by extension our activator, means that we have no control over the light and dark periods in our simulations, which also shows that, yes, it's actually better to have lower values concentration of our deactivator, the by extension of our activator, so as to retain controllability of the process. This shows that the optimization is not a simple one, because we do need to tune those parameters very well, and this would lead to a problem, of course, of discrete dynamic optimization problem. Now, the problem is that those simulations, in order to be performed, each of them for a photopolymerization process takes around 10 hours to run. This obviously is not the extent optimization for the simulation to set that line each of the dimension would take 10 hours. So the question here is, can we actually accelerate that? Out of the possible ways, one way to accelerate such processes is to take advantage of the quasi-steady state that we see is being created. And the way to do that is by creating a deterministic, stochastic kind of model where we use a lot of models to simulate the microscopic, to simulate the process and get information from this simulation, and at each period and at each point we actually use information to inform our microscopic model, and from this microscopic model to be able to use afterwards microscopic properties and gain information at the macro level. The idea then becomes simple. We can actually create, instead of a dynamic Monte Carlo, we can perform steady-state Monte Carlo simulations, again we're using a steady-state assumption, in order to be able to accelerate, to simulate each polymer perfectly, and thus get information about the microscopic properties of the whole population. And then, excuse me, this simulation, the steady-state simulation will have at each step of each period of the discretizing of the models, and we have as a result the habitable that almost takes care of the dynamics, while the steady-state simulation takes care of the microscopic information. This leads to an acceleration by 2 orders of magnitude, 3 or 2 orders of magnitude of our simulation, where we can now see that such a simulation gets us close to being able to perform later on optimization. And here now comes the next point, where this was the chemical engineering part. Now, if we actually change also, we change also the hardware, we can even accelerate the simulation even more, leading to 1,000-fold acceleration of such simulations, getting us now into the computational feasibility regime for our optimizations. So we see that if we have simulation of the dynamic of the reactor, we have microscopic scale, that is actually very slow. If we have to model that we accelerate, and if we actually change also the architecture, that the model simulation, so to say, the code architecture, we can accelerate even further our simulation. So, in conclusion, what we presented here was a way to for the 40 year accelerate simulations in order for us to reach the state where we can actually perform to perform our optimization and process engineering. This leads and opens to a host of different possibilities, where by performing the in silicon control reactor optimization, we can have, and by gaining mechanistic understanding, we can actually now perform a number of processes engineering tasks, such as optimize the process, which is what we will discuss today, even further perform a regular design, perform the recycling, the design, and high scale of production. With that, I would like to thank you for your attention.
Thank you very much.